Up until now, we've been making believe that we know that when we take a sample, oops, we take a sample from a population, from population A. Okay, let's say that's the United States. That let's say it's the amount of wine that's consumed in each state, like per month. In New York, it's 4 liters. In New Jersey, it's 3 liters. In Texas, it's 2 liters. In California, it's 5 liters. And in New Mexico, it's 4 liters. Okay, we have a sample. We've taken a sample of states in the United States or individuals or whatever we want to talk about. We're going to compare that now to France. Okay, except in France, we've actually done a survey of all the wine drinkers in France, and we know that the average consumption per month in France is, in other words, mu for the consumption of wine in France is equal to, let's say, 3.8 liters per month. Okay, well, that's very interesting. We know the population consumption for France. Well, that seems very unlikely, doesn't it? That we would know the population consumption for everybody in France, because in order to do that, they'd have to literally survey everyone in France. And while there are many surveys in France that probably track wine consumption, chances are they are samples themselves. They're not going to be the entire population. They're going to be a sample. So in this imagined structure that we have made, we said to ourselves, let's imagine that we know the actual population mu for that consumption in France. Now in the United States, we don't know it, but we're going to take a sample. And this sample indicates, let's see, 9, 11, 15, 18 divided by 5. Okay, it turns out to be 3.4 liters of, am I right? 3.6 liters per month. Okay, this is X bar. It's not a population sample. It's a sample, not a population mean. So now we want to compare whether Frenchmen drink more wine than Americans. Okay, well, we then used what we knew about central limit theorem, about sampling, and so on and so forth, to make judgments about the variability that we see in the United States and the average that we got for the United States for this sample. And we use that to create a confidence interval. I'm going to make believe that the confidence interval is 3.3 to 3.9. Okay, confidence interval for the mean mu for America, right? The mean, our estimate of the U.S. is 3.3 to 3.9. We said to ourselves, well, we're 95% certain, say 95%, we're 95% certain that the true mean consumption in the United States is between 3.3 and 3.9 liters per month. Well, in France, we know for a fact that it's 3.8. Well, I look at that and I say to myself, I'm saying to myself, we're only 95% confidence it's between these two numbers. So it's entirely possible that the real mean consumption for the United States is 3.8, just like it is in France. That's a possibility. That's within that range of possibility for our level of confidence. Had I told you that the consumption in France was 4.0 liters, we could say with 95% certainty that the two means, the true population means, are different from one another, mostly as a consequence of understanding the variability in the United States and the values that we got here. Okay, so now that's very interesting. We very rarely know what mu is. This has really been an exercise in starting to understand how the confidence interval works, how we compare means between two populations. In reality, do we ever know the mean for one of the populations? Not really, right? Usually, we're taking two samples. For instance, we might sample a random collection of American citizens, random collection of French or Canadian citizens, and survey them, and ask them for their wine consumption, monthly wine consumption. We may ask them about their smoking habits. We may ask them, do you smoke or not smoke? And instead of finding all of these cases, when I do that, let me go back up here. In all of these cases, when I do that, I'm not finding mu for one population and mu for the other population. I'm finding X bar for both populations, right? So I have a sample for this population, a sample for this population. Well, things are complicated now, because before, when we were in that other construct, right, we could make our confidence interval, and we could kind of represent it. We could represent it by showing a normal distribution, or for a sample of means for one of these two populations from this area to this area, and then just show where the other population lies in relationship to that distribution. Is it within the area that we would expect 95% of the outcomes, or outside of that? Well, now I got a much bigger problem. Now I have a sample for the first population, sample for the second population, and the first population has its own sample distribution that's centered around the mean. Second distribution has its own sample distribution centered around the mean, right? In this case, I'm showing them as being different. One population being different than the other population. However, we can see that there's overlap between the two of them, right? So, for instance, there's going to be a lot of Frenchmen that drink less wine than some Americans. There are going to be a lot of Americans that drink more wine than some Frenchmen. But in general, we're really interested in the average for the two populations. We want to see if these are really two different populations, or if really the two of them have roughly the same mean and it's really one population. Okay, this complicates things. It complicates things because, for instance, before, the way I used to evaluate my sample is I'd find my X bar, then I'd find my standard error. Right? My standard error was going to be equal to the standard deviation over the square root of the sample size. Okay, and that's for a list of numbers. I'll just 3, 5, 3, 4, 5, 4, 3, whatever it was that we had before. Right? This list of numbers is going to account for my standard deviation and my sample size. Okay, now I have a problem. I have another sample, and that's a different list of numbers. 4, 6, 7, 3, 4. And this is going to have its own standard error, right, based on its standard deviation and its sample size. Well, now things are complicated here now. I want to see if these two means, or at least the population means, are equal to one another, or if they're really different. So now, one of the complications here is I got two means, not one mean. So instead of looking at it as two means, what I'm going to look at it as, I'm going to look at it as a difference between these two means. I'm going to say X bar 1 minus X bar 2, right? Or remember, this is a substitute for mu 1 minus mu 2, right? That's kind of really what we're after, but we only have the calculated means to deal with. If these two populations are the same, what would I expect mean 1 to be minus mean 2 to be equal to? Expect it to be equal to 0, right? Okay, so I'm going to start with my null hypothesis, being that the two means, if I subtract one from the other, the difference is going to be 0. So what's my alternative hypothesis? That mu 1 minus mu 2 is not equal to 0. It's either bigger than 0 or smaller than 0, right? So now, okay, that's what I'm after. So I'm not really interested per se in the individual values, but in the separation between the two means. Okay, so now if I'm gonna go ahead and try and figure that out, well, I can figure out the difference between the two means. Let's say that this is 3.5 and this turns out to be 4.2. Okay, difference between them is 0.7. That's my difference, my average difference between the two of those things. Well, I want to show that that average difference is, I want to know whether that average difference is really different than zero or is the same as zero. If it's different than zero, I can reject my null hypothesis. If it's not different than zero, I can't reject my null hypothesis. So in order to figure out if it's different than zero, I have to know how variable it is. And what gives us a measure of the variability again? The standard error, right? So how do I calculate my standard error? Well, I got a problem. I got two sets of numbers. I got this set of number and I got this set of numbers. A lot of things can be happening here. One thing that can be happening is that the variance in this group is the same as the variance in this group, right? That'd be very convenient, right? Because I can pool the two of them and get a better estimate of where the standard error is. Okay, well, or standard deviation is. Okay, well, it could also be that the variability in this group is much lower than the variability in this group. Well, then which variability should I use? How should I resolve that? That's our issue here. We're going to wind up now with several conditions here when we go to compare two means based on samples, right? We're going to have a few conditions. One of the conditions is going to be, okay, mu1 minus mu1 and mu2, and with equal variances. Okay, the other condition is I have mu1 and mu2, and they have unequal variances. In the lecture, you noticed that there were different formulas used for the standard error based on whether we were assuming equal variances or unequal variances. How different do the standard deviations between these two samples have to be to assume unequal variances? Anyone want to take a guess? That's not an easy question to answer, right? Because they're always going to be different. How different is too different to assume equal variances? That gets a little complicated. Sometimes they say that if it's less than a factor of two, just assume equal variances. That one might be one good way to handle it. There's a problem with that, though. One of the sample sizes may be much bigger than the other sample size. So shouldn't we stick to the bigger sample size because it gives us a better idea of the variance? So sample size may be a consideration. So it gets a little complicated, which one of the two that we're going to do. Not only that, but the formulas get very complicated as well. Remember the formulas that he had up there for pooled standard deviation and for equal and unequal samples, calculating the degrees of freedom. One of them, the degrees of freedom calculation, was just ridiculously complex, right? So this could get very complicated. We're going to avoid, for tonight, we're going to avoid that complication. We're gonna work with samples that we're going to be able to use SPSS to solve for. So it's going to give us a little bit of an exercise with SPSS, give us an introduction into comparing two groups, two means, when we have the sample of both. And then later on, as we work through this, maybe we'll have a session like like a pre-homework session, where we can go over some of the homework problems. There's an extensive homework that just got posted. It's not due until 3 weeks, but maybe between now and then, we got the spring break and so on and so forth. But yeah, we get homework. I mean, the semester's not over yet. What's this? To be honest, which is a very large problem set, but you got a lot of time to do it. Not all the problems are things that'll take up a lot of time either. So at any rate, but between now and the next time we meet, maybe we can have a couple of one or two sessions online where we can take a closer look at this and work things out a little bit more directly by hand, as Levi has done in a couple of examples on the board there. But for now, let's let SPSS do the heavy lifting so we get an understanding of how this works, what kind of answers we're going to get, what kind of analyses we're going to do. Okay, so I'm going to open up. I'm going to, even though I said let's use SPSS, there was one other possible situation which I didn't mention, and that is certain situations where we're looking at two groups or two populations, right, or two possible outcomes, and we're actually dealing with things that are related. For instance, if I were going to test a drug on you, and say something that lowers blood pressure, right? Let's say I gave you the drug for 2 weeks, and I then tested your blood pressure. Then I gave you 2 weeks off with a placebo, right? You don't know which one you're getting first, the placebo or the drug. Then you take a placebo for 2 weeks, and I test your blood pressure again. Okay, placebo, and 2 weeks I test your blood pressure again. Next guy, you don't know which one you're getting first, but you spent 2 weeks on the drug, 2 weeks on the placebo, and I test your blood pressure. But I test your blood pressure before we do anything, right? And I look at the difference between your blood pressure on the placebo and your blood pressure on the drug. And I find that the drug lowered your blood pressure 10 points, and the placebo lowered your blood pressure. Maybe was kind of like a placebo effect, lowered your blood pressure 4 points. Next person, the blood when he was on the drug, his blood pressure was lowered 6 points, and when he was on the placebo, no chance, same thing, same 6 points, lowered it. These are minuses, right? Let's say the next person lowered his blood pressure 8 points when he was on the drugs. When he wasn't on the drug, it lowered it 7 points. Okay, so now these numbers represent values before and after, or drug or no drug, for the same person. So for you, you may have started with a blood pressure of 110, right? So it lowered it to 100, and the second time around lowered it from 100 to 104, and so on. Now let's say that this next person started with a blood pressure of 130. Well, that's a different person. Maybe blood pressure is higher. It might have the drug or the placebo might have a different effect, a larger effect or a smaller effect. It's different than if I took 10 people and gave them the drug and took 10 other people and gave them the placebo. Now I'm eliminating a lot of variables by testing the same person twice, before and after. That's called a paired sample. In that case, I got 2 samples, and instead of looking at the average for the drug group and the average for the placebo group, what I'm going to look at is the difference for each individual. Like the difference for this person was +6. Different for this person was 0. Different for this person was +1 between these 2 effects. Okay, so I'm going to look at this and say to myself, I'm just going to average the difference, find the average of the difference. Now, if there's no difference between the placebo and the drug, I'd expect that difference, the average difference, to be 0. I'm going to analyze that as if it's a single sample compared to 0. So when I'm working with paired samples, even though it's really 2 samples, same person before and after, for instance, then you can just look at the difference for each individual and just look at those differences as if they're a single column of numbers, and you're going to compare it as we did before to a single number, in this case, a difference of 0. Okay, so now that's a lot more that's a lot more flexible, a lot more easy for us to evaluate than if the paired samples are 2 different groups of people, and we got to deal with the standard deviations being different, and so on and so forth. So a little bit more direct, still two separate samples, but this case, each individual, looking at the difference for each individual. Before, we were looking at the differences in the means, X bar 1 and X bar 2, right? And then we had to use the variances to figure out, if we should be sure they're really different. Okay, so we're going to take an example of that to start off with. And on Blackboard, we have an Excel file, right, which is called serial. Serial Excel file. That's what this file looks like. Okay, how's that look up there? Is it readable up? Oh no. The back yet? No. Hold on a second, you guys online? It's back? Okay. I forgot, I usually turn off the screensaver. I forgot to turn it off tonight. Okay, so here we go. So this is a study where we're looking at how cornflakes and oat bran, both of which presumably make claims about reducing cholesterol, how much they reduce cholesterol after someone's been eating them for a month. Okay, in each case, this is subject number 2. This is a monthly. This is the reduction he got by eating cornflakes for a month. This is the reduction in cholesterol he got for eating oat bran for a month. Now, we don't know if he ate in this study. We can't tell from the way this data is listed whether he ate the cornflakes or the oat bran first. Obviously, it's going to be randomized for all these individuals. Next guy dropped 5 points and 6 points respectively, and so on and so forth. But each one of these rows represents a different person, right? So I'm going to say to myself, my null hypothesis is that the difference is equal to 0, right? That the difference between the amount that your cholesterol was reduced by cornflakes and the amount by oat bran is 0. It's the same amount, right? It's got to be the reduction. And my alternative hypothesis is that the difference is not equal to 0. Okay, so now I have to go back here and prove it. So now instead of looking at this as 2 separate groups of people and going down here and saying the average for that group is this, and the average for that group is this, and then trying to compare them the way we're going to be doing in a minute for 2 samples that are not paired, right? Instead, I'm going to look at the difference for each individual. For this person, the difference was, okay, minus 0.77. And then I'm going to do the same thing all the way down. Okay, so what's the average difference? The average difference is equal to, okay, it's equal to minus 3.6226. It looks like that would mean that oat bran actually lowered it more than cornflakes did, right? Because it's this number minus this number turns out to be a negative number on the average. Okay, so what's the standard deviation for the differences? Standard deviation for the differences is going to be just a standard deviation for these numbers. Okay, is 0.4. What's the standard error? Well, the standard error is equal to the standard deviation divided by the square root of the sample size. What's the sample size here? It's 14, right? Am I right? Or is it 15? 14. Sample size is 14. Okay, that's our standard error. How many degrees of freedom is this? 13. Okay, it's a small sample. What am I going to have to use to count? Am I going to use the z-score or the t-score? I'm going to use the t-score. So in order to use the t-score, I'm about to calculate the t-score. Anybody remember the formula for calculating the t-score? It's equal to, what is it equal to? It's, right, it's equal to x bar, right, minus the mean, okay, divided by standard error, right? Okay, so I'm gonna just do it that. Whoops, just gonna do it that way, just so we have something to look at. Okay, so I'm gonna look at the difference between the mean and the value I expected it to be, which was 0. So that's going to be equal to this number minus 0 divided by. I'm gonna put parentheses in there. It's obviously minus 3.6 divided by the standard error. Okay, it comes up to a t-score of 3.34. It's a negative t-score. We don't care about that because we know that, it could go either direction. The t-score is the number of standard errors away from the middle, so away from the other value, so that we know how far out it is from the expected values. Okay, so what's the probability of getting that large a t-score? Well, first of all, let's look up what the critical value of t is for 13 degrees of freedom. Okay, so I'm going to go look at my t-table. Okay, let's see if I can't find it. Crusty. There we go. There it is. Okay, here's my t-table. So 13 degrees of freedom for a 95% confidence level or a alpha of 0.05. In other words, 0.025 in each tail, 2-tail test. It's going to be 2.16. In other words, I have to exceed a t-score of 2.16 to reject the null hypothesis and only have 5% chance of being wrong and rejecting it improperly. So what I say was 2.16. 2.16. So can I reject the null hypothesis here? Right? Is 3.34 bigger than 2.16? Yes. So I can reject the null hypothesis and say that oat bran, indeed, is a difference between oat bran and cornflakes in the amount of reduction in cholesterol that you can get from them. Okay, probably not clinically significant, but it's statistically significant. Now, what's the probability that we would get this low a t-score? Anybody remember how we might do that in Excel? Which one is it? T-test? T-dist or T-test? Let me try both. T-test, parentheses, array. Nope, that's not the one I want. How about T-dist? Parentheses, up, let's see, X. My T-score is negative 3. I'm going to put that in there for X, comma, degrees of freedom is 13, and comma, tails, 2 tails. See if that gives you, oops, I made a mistake there. X value, negative degrees of freedom, tails. Oh, no, I don't think this is what I want. I don't remember which function to use. Let's see, t-test, t-dist, t-value. What does that do? See what that does. Nothing. Little t. T dot test. Array. Nope. That's for 2 groups. T-dist. Parentheses. Let's see if that 3.34 comma 13 comma 2. Oh, you know what happened? I think that they're blasting me here on the online here. It has to be a positive number, eh? Sound levels breaking up. Okay. I think what happened was when I did it the first time, I might have put like a period instead of comma, right? I don't think it makes a difference if I put a negative or a positive. In fact, I'll put a negative in here this time. See if that makes a difference. Oh no, it didn't work. That's weird. You would think it'd be smart enough to figure that out, right? So the probability of getting that big a t-score, if the difference is really 0, right? Well, the probability is less than 1%. It's 0.005. Okay. Everybody at least reasonably comfortable with that so far? Okay. So I looked up that probability using Excel. Normally, you wouldn't have bothered to go any further than finding the t-score and saying it's larger than the critical value, because that already is you've achieved your objective of rejecting the null hypothesis at that level of certainty. 95% certainty, alpha equals 0.05. In other words, 5% chance of being wrong. This tells you that it's even below 1% chance of being wrong if you reject the null hypothesis. You guys okay at home with that? Does that seem reasonable to you? I'm going to do the same thing now, except I'm going to use SPSS. There's another file on here called serial. That's an SPSS file instead. So I'm going to go here, and I'm going to open. Let's see. Okay, let me try and find it here now. But it's on Blackboard in the lab lab 3 and 4 section. And let me find SPSS here. Here it is. Okay, wait for it to open. Okay, open. Data. Oh, actually, I think I may be able to get to it by recently used files. Here we go. Let's see if it opens up for us. Bingo. Same file we had before. Okay, now, what am I going to do when I want to compare means in SPSS. Before, what have we learned so far? We've learned a couple of things about SPSS. Number one, that we have two views of the data in SPSS. We have the view that we have here, which is the data view, and then we also have the variable view, where it explains the variable name, various parameters, various properties of that data, and so on and so forth. This is a scalar, it's a numerical variable, right? So we're going to stick with the data view for now. So, so we can look at the data here. And now we have it input, cornflakes in the first column, operan is in the second column. Okay, we want to compare the reduction of these two different materials. The only difference here is that we know that it's the same person that's represented in both those columns. This is how much cornflakes reduces cholesterol. This is how much operan reduces cholesterol. Subject number 4, how much cornflakes reduces cholesterol, how much operan reduces cholesterol. So I want to compare the difference of these two groups, right? So I'm going to go up to analyze, and before we generally stayed in this area here called descriptive statistics. We used frequencies, we used descriptives, we used explore to find all our various descriptive statistics. This time, we're going to go a little further, from analyze to compare means, right? Naturally, right? Analyze, compare means. Now, a lot of people have struggled with SPSS. How much easier could this be, right? We're going straight to analyze, straight to compare means. Now we got to make a decision. We have a few choices here. Compare means, one sample t-test, independent sample t-test, paired sample t-test. We used one sample t-test before, didn't we? When we had a sample and we want to compare it to a certain number, right? We've used that. That's what we were doing up until now. Now this time we have, in this case, what do we have? We have a paired sample t-test, right? Two groups of numbers. I'm going to click on that. Okay, and notice it opens up in a browser window where I can move over, just as I always can. It gives me the opportunity to identify what variables I want to work with. It lets me move over the two variables into a pair. It's expecting a pair of numbers, two columns of numbers, not one column of numbers. So I'm going to move over cornflakes, and then I'm going to move over operan. Okay, and it puts them in there, and it waits for us to put both of those in there before the OK turns blue. I don't think there's anything we need to look through in options. Options by default is 95% confidence, which is the same thing as an alpha error of 5%. We're 95% sure we're right, means we're 5% or less percent sure that we're not wrong. Okay, so I'm going to leave that just the way it is, 95%, and I'm going to click OK. Okay, and it's going to go through all the analyses. It found the mean for one group, found the mean for the other group, found the standard deviation, standard errors, and so on and so forth. And then in the paired samples t-test down here, it really didn't use that. What it did then was it says, okay, let's take the differences between all of those, and it finds that the mean, see paired differences? It finds that the mean difference is minus 3.62. What did we find? Same thing, I think, right? Okay, hopefully, I hope we found the same thing. And what was the standard deviation we found? 0.40, same thing as they found. What's the standard error, which is just the standard deviation divided by the square root of the sample size, which is 0.108, same thing we found. What is the t-score that we found? 2 is minus 3.344, the same thing we found. Degrees of freedom is 13. And what's the probability for a two-tailed test that we would be wrong if we rejected the null hypothesis? The p-value, in other words. The p-value, the probability we would be wrong if we reject the null hypothesis is 0.005. That's also another way of saying that. What's the probability that we would have this outcome, this big a t-score, if there were really no difference between the two serials? Well, there's less than a 1% chance of that. That less than 1%, that's our p-value. Now, what is that significance or p-value have to be less than in order for us to be satisfied that we're not wrong? It has to be less than alpha, which is, in this case, what's alpha? 0.05. right? Everybody get that. 0.05 is our alpha. If that significance or p-value comes out less than 0.05, we say we reject the null hypothesis. We say there's a difference. Okay, this is great. It did all the work, right? I mean, like what could be better? Now, let me ask you something else. What if this sample had not been a paired sample? Okay. What if this sample had been one group of people that ate cornflakes and another group of people that ate oat bran? Could I call this a paired sample? No, I couldn't. There are two samples. One group of people eating this, one group of people eating that. Those are independent samples, right? They're not dependent on each other. It's not the same person. They're independent samples. It's two means that we have to deal with. So now instead, we have to find, if we were going to do this by hand, we'd have to find the mean of group one, have to find the mean of group two. We'd subtract the mean of group one for the mean of group two, divide it by the standard error. The standard error now is complicated because I have two different groups. I got to decide whether they're equal variance, unequal variances, what the degrees of freedom are, and so on and so forth. It gets complicated. For tonight, we're not going to delve into that complication. We're going to let SPSS do the work. This time, it's not paired samples. How am I going to analyze this? Go to analyze, go to, where do you think? Compare means. And instead of, it's not a one sample t-test like we did in the old days, not a paired sample t, it's independent samples t-test. Okay, I'm going to take that. So now the test variables, now I got a problem here. This data is not set up properly for me to do this because it'll let me find the means and all the stuff for cereal and oat bran and so on and so forth, but it won't let me compare the two groups. The reason for that is SPSS doesn't like the data in this format. I'm going to use Excel now to change this data. Actually, let me see if I can't do it right here. I'm gonna try it right here. I'm gonna say cut. Let me see if it'll let me do it. Edit, paste. No, it doesn't let me do it. I don't know if that's it. This is a bug. Oh no, let me do that. Okay, you have to. It changed all those values. Yeah. SPSS is a mess this way. I'm gonna do it again. I'm gonna go back to Excel. What's that? You can use the transform function is really meant to create new variables, compute new variables, and so on and so forth. For the moment, I'm gonna do it a slightly different way rather than involve that for right now. We'll get to the transform variable. I'm gonna go back to Excel. And instead of the top values here are cornflakes and oat bran. I'm going to delete that. Delete. Well, actually, I'm not going to bother to delete that. I'm going to take these numbers, cut rather, and I'm going to paste them down here. Okay, and everything from 15 up is the value. I'm going to give it a value 1. That value is going to represent cornflakes. Fill up. Oops. Try it again. Down to 15. Fill down. Okay, and from 16 to 28 is going to be oat bran, and I'm going to give that a value of 2. Fill down. Okay, so now, see, this is the same data as we had before. Exactly the same data, except now the variable here is going to be the type of cereal. Okay, and the variable here, the variable here is going to be cholesterol reduction. And the variable here is going to be the type of cereal. Oh, I can't have any spaces. I'm sorry, did it again? Okay, type of cereal. Can you see it yet? Okay, good. That's going to be, notice I didn't put, it started with a letter. I didn't put any spaces or any weird characters because SPSS is about to import this. So I'm going to save as, and I'm going to call it serial special. See, if I had realized I was going to paint myself into a corner, I didn't know I was going to use this way. It just occurred to me to use this file this way as we were doing it, but I didn't really prep a file for it properly. But that's okay. You would see how I would do it anyway. So now I'm going to open a new database. New data, file, new data. I'm going to tell it that I want, file, open data. Okay, I'm going to navigate to desktop and to, let's see where I put that thing. First of all, I got to tell it to look for Excel files. Okay, and I think it's in that area here. And here's serial special. That's the one I just made. And I'm going to tell it import that Excel file. And it's going to think about it for a second. It sees data between A1 and B30, which is what we expect. And I say, okay. Also, that little checkbox said, read the first line as the variable name. And sure enough, the first column is the amount, is cholesterol reduction. The second column is the serial type. It's ones and twos. Now get this, I'm going to go into the variable view now. And see the serial type here? If I go into values and click in there, notice I get a little gray box here I can click on. I'm going to go in there and tell it one, the number one represents cornflakes. And the number two represents oat bran. So now SPSS has learned what those values 1 and 2 represent. If I go back to the data view, right, it actually presents it to me. If I don't want to see that, I just want to see the 1s and 2s, I can just click off value labels, and it'll go to 1s and 2s or turn them back on. But it's buried there. SPSS knows what those are now. So now I'm going to go into Analyze, Compare Means, Independent Samples, right? And it's asking me for the test variable. Well, the test variable is really our cholesterol reduction. And it's asking me for the grouping variables. How should I group these two groups of data? I want to group them by the type of serial. So it's going to compare, it's going to look at the data as two groups, two different kinds of serial. Options are still going to say 95%. That's fine. I got to define the groups. It says, okay, it says type of serial is going to be the grouping variable. Define the groups. Well, SPSS is not very bright this way. You would think it would be able to figure this out for itself, but you actually have to tell it that the groups are 1 and 2 and click continue. Right? So now it knows what the two groups are. The reason why it does that is because sometimes that grouping variable can have more than two values. For instance, if you're comparing ethnicities, you could have many ethnicities and you want to compare two of them, you can pick out, well, give me number 3 and number 7 to compare the two means of, right? So you can just tell it 3 and 7. In this case, it's only 1 and 2, so you would think it would be able to figure it out for itself, but unfortunately not. So I'm going to click OK. So it's going to do an analysis now. It's going to find the mean of each group, going to find a standard error. It's going to find it both ways. It's going to assume equal variances. It's going to assume unequal variances. Why is it going to do that? Because it's a machine. It can do it in an instant anyway, where we would make a decision ahead of time which way we're going to handle it because we don't want to do that, laborious calculation. Okay, I'm going to click OK. Okay, and see what we get here. Well, the mean for cornflakes was a 4.08 reduction. The mean for oat bran is 4.4 point reduction. Okay, standard deviation, standard error for each of the two groups is calculated. Okay, and they look pretty much the same, don't they? The standard deviations, right, and standard errors. They're very close, certainly under that multiplier of 2. So I'm going to get to the guys online, make sure they don't have any problems here. So now I'm going to go over here and I'm going to look at my box here with my independent samples test. Okay, and I'm going to look down here and I'm going to say to myself, let's see, I got two choices here. It did it twice. It did it once with equal variances assumed, and it did it the second time with equal variances not assumed, right? Well, which would you say is kind of a null hypothesis here, the default value? Equal variance is assumed, right? Sounds like our null hypothesis. So we're going to stick with this top row. See, it does the calculation twice. We're going to stick with this top row unless we have a reason to think that they're unequal variances. Okay, there's two ways for us to do this. One way is by inspection, it looks like it's equal variances. Standard deviation of both groups is the same, right? It also, SPSS actually does a calculation. And the calculation calculates something called a Levene's test for equality of variances, and it calculates a score called an F score and a significance. That's a p-value, right? In order to reject the idea that we have equal variances, what do you think we want that significance to be less than? Take a wild guess. 0.05, right? We want to have less than 5% chance of being wrong before we reject the idea that they're equal variances. What is that significance? What is that p-value? 0.66, way above 0.05. So we're just going to stick with the top row, just the way we would expect it that we thought we were going to stick with the top row. So I'm going to go across. What's the t-score that we got? Negative 0.47. Don't look too promising now, does it? Right? And the degrees of freedom now are 26, right? Because remember now we're dealing with, two separate groups, right? With equal variances, right? So it's N1 plus N2 minus 2 is the degrees of freedom. The significance, two-tailed significance is how much? 0.352, 0.35. What did we say that significance has to be for us to reject the null hypothesis? That the means are equal? Has to be less than 0.05, right? Is it less than 0.05? Do we reject the null hypothesis? No, we fail to reject the null hypothesis. Is this data any different than the problem when we did this paired samples? It's not. It's the same numbers. What caused the difference? What caused the difference is that we had a lot. The data was a lot more reliable, removed a lot more variability, where we'd be able to take readings for the same person before and after, or in condition A and condition B, than if there were different people that we had to account for in the two groups. Everybody agree with that? Everybody see why that we have more power in paired samples than we do, because if the samples are not paired, in other words, person one before and after, if they're a smoker before, they're a smoker after. If they're overweight before, they're overweight after. Look at all the variability that are taken out, not just the numbers, but also all the confounding factors get removed from this whole thing when you do a paired test, right? When you do that kind of study. I just want to go online, make sure those guys are doing okay. 0.352 is greater than 0.05, so we fail to reject the null hypothesis. Yeah, it's a little bit easier than doing hand calculations, right? That's why I want to do this first, and then I want to move on as we go forward. Like over the next couple of weeks, I want to move on to actually maybe doing a couple of videos or going online and doing a few examples by hand. So it's less than if it's less than 0.05. Hang on a second, guys. Peter, there's two issues here, Peter. One is that are the variances equal or unequal? Okay, so we got two rows of results. SPSS actually does. You see in the box here, we actually have two results: the top line and the bottom line. Okay, as it happens, the t-value we calculated was the same in both. Okay, the top line and the bottom line are two sets of separate results. The top line use the formulas that assume equal variances. The bottom line assumed unequal variances. As long as this first box here, 4x4 box here, as long as the significance for this test for variances is greater than 0.05, we fail to reject the null hypothesis that the variances are equal, so we stick with the top line, equal variances. If this were less than 0.05, we'd use the bottom line. Some cases it'll be quite a bit different. A lot of cases it won't be different, but we would use the bottom line. So in this case, since this is greater than 0.05, we stick with the top line. But then this other significance here, this is the t-test for the equality of the means, is this whole rest of this section, separate from the Levene's test for equality of variances. Okay, if we look there, the t-score for the equality of the means is only like a t-score of 1. Not a very big difference a big enough difference between the means to say they're different. This is the number of degrees of freedom. This is our significance, our probability of getting this outcome if the means are indeed different, not different from one another. So there's a 35% chance we could get this outcome if the means are not different from each other. So we want that chance to be less than 5% before we say the means are different. So if this value, the two-tailed significance or p-value for our t-test for equality means, if that is greater than 0.05, we fail to reject the null hypothesis. If it's less than 0.05, we reject the null hypothesis. Okay? Does that make sense to you guys? All right. So I'm going to move on to another example of this. Yes.
Why do SPSS calculate value for the equal variance model for F and the why wasn't there values for those?
I'm sorry. No, it does. See this test. This test is just analyzing the variability between the two groups. So it's comparing the two groups. So it only has to do it once. In other words, imagine it this way: I'm comparing Fred to Mary. It's the same thing as comparing Mary to Fred. Yes. Oh, no, no. What I had said before is one of the rough rules that you might use is that if the variability of one group is twice the variability of the other group, you might say that they're, like in other words, the standard deviation of one group is 10 and the other one's 20. You might say, I'm thinking they're unequal, but that's really a rough rule. There's a million other factors to consider, maybe I should choose this one because I have a sample of 50 in this for this group, only 10 in this group. So, and I think probably there's no reason for them to be different. The variability, not the actual means. So maybe I should just stick with the bigger one. So there's a lot of judgments that you can make on it. Sometimes it's just easiest to let SPSS make the judgments for you. Okay, so let's try another example. Well, first of all, number one, we are at about 8:10. I know the final is on tonight. And I understand people want to see it. And this is going to be on, I'm recording this. This is going to be on uploaded later on. If any of you guys want to go catch the game and pack it in for tonight, I will understand completely. I'm going to continue for another 20 minutes, 20 or 30 minutes. So if you want to stick around, you can. But if you want to catch the game, fine, because you'll be able to watch the rest of this. I'm going to repeat this with another data set, and we might see a different result and stuff like that. What's that? Those who want to watch the game stay at home. Well, but they're home, or the game doesn't start until 9. If you're here and you got to take the train home, you might not. Huh? They're gonna get to see the game anyway. What game? Very good, Jessica. That they call it March. You ever heard of March Madness, Jessica? Okay. So at any rate, it's not the Met game. I'll give you a hint. It's not the Met game. That's for sure. Okay, so I'm going to open up another data set here. Okay, let's see. Open data.